Okay, so let's review last time, the last thing that we stopped at. If you guys remember, last time we started talking about discrete and continuous random variables. And that's actually one of the basics of engineering reliability. It's all about random variables. All the quantities that we are dealing with is random variables, and we are taking everything that we learn to the next level. Like nothing is deterministic values, like loads, strands, any value that we are dealing with is a random variable. And this is where all the risk factors, or what we call the over strength factors or the safety factors coming from, because of our uncertainties about the variables that we are dealing with. So the more uncertainties that we have, the more safety factors is going to get bigger. Okay, so let's revise what we stopped at last time. I'm going to continue on the continuous random variables. If you guys remember, so continuous random variables, we usually simulate them with a distribution, something like this. And the thing is, if you try to get the probability of a specific number to happen, usually the probability is the area under the curve. If you guys remember, it's the area under the curve. If you try to get the probability under just this point, it's going to be 0. Okay, so that's why we usually deal with the cumulative probability, so that we can get the probability of x is less than a. But the probability of a itself is 0 because the area under a is 0. So that's why we take it from a derivative like point of view. Like, all right, I'm looking for my number, which is x, and let's assume that is x is like this area, and if I take this area out and make it bigger, it's going to be something like this, and the width of this is dx, which is almost 0, and this is the random variable that I'm looking at, and this is actually still the random variable that I'm looking at because this distance is very small, and let's call this delta x. Dx or delta x both are the same, plus delta x. And here, the probability of this random variable, as we said last time, the exceedance, I mean, fx is going to be the exceedance probability, x, and this is for random variable x, and this one is fx of x plus delta x. And I told you last time, what does this mean? Do you guys remember? That means the probability of my random variable x to be less than a specific value x. Like, what is the probability of my wind speed v is less than 30 miles per hour? So this is my random variable that I don't know, and this is the assigned value that I'm looking at. Okay, so, and we said that if we want to find out fx of x, and fx is small, this is the probability of my random variable to be equal to the assigned value. Okay, so that is the difference between both of them. So this is going to be the limit when delta x approaches 0 of fx of x plus delta x minus fx of x over delta x. So that's what we have from last time, and we said that's actually the definition of differentiation. So this means that this is equal to ddx of fx of x. All right, so that's what we stopped at last time. So if you want to find out what is the BDF from a CDF, cumulative density function, and you want to find the probability distribution function, basically you differentiate the CDF so that you can get the BDF. You need to familiarize yourself with the abbreviation, like the BDF, CDF, F small, F capital, because that's what we are going to use the whole course. Okay, so since we have that fx of x is equal to the derivative, so if you integrate both sides, like if you integrate this side, you are going to get rid of the differentiation. So fx of x is going to be equal to the integration from negative infinity to the variable that I'm looking at, like let's say here, x of fx of x dx. All right, like if you are looking for the probability of x to be less than x, like let's say this is my x, I'm looking for my random variable to be in between negative infinity and x, so you have to integrate this function over this curve from negative infinity to x so that you can get the probability of x to be less than or equal x. But so that I can my final integration to be in terms of x or as a function of x, and I don't get confused with the variables, I can make this exceed and this exceed. And let's say that my function is x squared plus 2x. Rather than writing that way, I'm gonna make it xc squared plus 2xc. So once you integrate it, this is gonna be xc cubed over 3 plus xc squared. And once you integrate it, you are gonna substitute with the boundary of the integration, and then x is gonna show up again, okay? So it's the same thing. All right, so let's continue on this concept. Right now, I'm gonna define something. We are gonna start a new thing, but this have to be in your brain. We have a BDF and we have a CDF. The BDF is the probability density function. It shows you how your random variable is distributed, okay? And if you wanna find the BDF from the CDF, you have to integrate this over the boundary conditions that you have. So if your x is here, you integrate from negative infinity to x. And if you have the CDF and you want to find the BDF, you have to differentiate this function, okay? All right, so right now I'm going to talk about something called jointly distributed random variables. So what is the jointly distributed random variables? It is two variables that are dependent on each other. Like let's say, I know all our class is males, but let's assume that we have females in the class. So we have males and females. That's a random variable. The gender is random variable. And let's talk about how they have things together. Like let's say the other things that I'm looking at, their favorite color. So the males have favorite colors and the females have a favorite color. So that's the two random variables that we are looking at the same time. The gender and the favorite color, okay? So something like this, like let's say also gender and favorite movies, okay? So all these are two random variables that are dependent on each other. Like let's actually I already made an example yesterday. It wasn't in the notes, so it's better to write it because it's in the notes that is uploaded already. So if I have here male and female, and here I have the favorite color red, blue, green. And let's say that we have, how many people are we looking at? 300 people. Yeah. So I have 300. I made a survey of 300 people. Okay. So out of these 300, I found that 90 males has favorite color red, 50 has favorite color blue, and 20 has favorite color green. And red females, I have 20 has favorite color red, 60 blue, and 60 green. That's a discrete random variable. Why? Because it's not continuous. You have a specific points, and the thing is, if you try to capture them in XY axis, actually you can do this. Like you can have an X-axis and Y-axis, and the X-axis may be the gender, and on Y-axis you can have the favorite color, and here is the probability. So here you put some, like I have only 2 genders, so I can say that I have number 1, male and female, and then I have here 3 colors. You have red, blue, and green, and then you'd start like find out the probability. But to find the probability for each one, so how can find the probability of a male that is his favorite color is red? Do you guys know how can I do it? Like let's say I put 300 people in a room and I picked one and I'm not looking what I'm picking. What is the probability that a one that I pick is a male and his favorite color is red? It's basically 90 over 300. Okay, so if you divided 90 over 300, it's gonna be 0.3. And this is going to be 0.167, and this is going to be 0.067, 0.067, and here 0.2, and this is 0.2. All right, so that's what we call joint probability, that you have 2 random variables melted together, dependent on each other. Or you have a sample space that has 2 variables, and we are trying to look or trying to represent how they are connected together. So let's see how's the CDF look like. So basically, if you have a joint probability, let's first talk about number 1, discrete random variable. So discrete random variable, if we want to write the equation of the probability mass function, when it comes to discrete, this is not called BDF, it's called probability mass function, BMF. The BMF. What is the BMF? The BMF is what is the probability of your reverse random variable x to be equal to a specific value xi, and a random variable y to be equal to a specific value yi. That means, what is the probability that I will pick somebody, like the probability of 2 things to happen together. The probability of a male to have a favorite color red and a female to have a favorite color blue. Okay, so that's this plus this. So we can write this as the probability, and I put x and y here, and here I put the 2 random variables, xi and yi. So I can write it that way or that way. If I want to write the CDF, the cumulative density function, so that is the probability of x, rather than I say equal, so it's going to be x less than or equal to xi, and y is less than or equal to yi. Okay, and I can write this the same way, but when I write this, I write it as f capital, fx and y, and I put this as xi and yi. All right, so this is how I write the BMF and the CDF. Okay, so that's the first thing about discrete random variables. Let's talk about continuous random variables, kind of similar to this concept. Continuous random variable. For continuous random variable, it's gonna be the same thing, but rather than having this as a b, so I'm gonna have like f, x, y. Look at this. This is the continuous random variable if you only have one random variable. But if you have jointly distributed random variables, this is gonna be, look at this. This is gonna be of x, y. That means the probability of x equal to x and the probability of y equal to y. This is x and y capitals are the random variables, and x small and y small are the assigned variables. So just to clear the confusion, like let's say that this is my random variable number 1, and this is my random variable number 2. So that's the x capital, y capital. The assigned value, 90 and 20 and 50, that's the x small and y small. Okay? All right. The cumulative distribution, the density function, I can write it that way, of x and y, and that means the probability of your random variable to be less than or equal this, and y is less than or equal small y. So that's how the BDF and the CDF look like. All right. So I want to do something like this, trying to find the differentiation or the derivative relationship between the two variables. As we know from here, we will able to prove that if I differentiate the CDF, I will get the BDF. If I integrate the BDF, I will get the CDF. It's the same thing applied for jointly distributed random variable. But since I have two variables, rather than having first degree differentiation, I'm gonna have the second degree integration. So I have to differentiate twice. So fxy is gonna be equal to the second derivative of fxy of x and y over partial x partial y. So I have to do partial differentiation with respect to x and y. Do you guys remember the partial differentiation? We already have done partial differentiation before. If you have a function of two random variables, you can differentiate it with respect to the first variable and with respect to the second variable. So that's what we should do if we want to find fxy out of the f capital xy. You have to differentiate fxy with respect to x and with respect to y. Okay? And it's the same thing with integration. If you want to find fxy capital, you have to integrate twice, from negative infinity to x and from negative infinity to y, fxy of x and y I'm gonna write it x and y first, then I'm gonna split it small. Dx, dy. But not to mix the variable, I'm gonna delete x, erase x and y, and replace this with different symbols. So I'm gonna make it u and v, and here I'm gonna make du, dv. So once you finalize the integration, substitute with the boundary in x and y, this is gonna return back as a function in x and y. Right? So that's if you have jointly distributed random variable. Okay? And actually the shape of this function is gonna be something 3D, as I write here. Like this is a discrete random variable. So if you try to, which one that have the highest probability? Okay, let's put right. The one that has 60 is the, okay, I have 90, so I have this is 0.3, which is the highest one, something like this. And then I have, this is a little bit small, and then this is 0.2 and 0.2, and this is 0.167 and 0.167. That's how the discrete random probability look like. It's a 3D. Rather than having a 2D, it's right now 3D. But what this is for discrete random variable. What if I wanna see how's the continuous random variable look like? So continuous random variable is gonna look like let's say that this is my variable x and this is my variable y, and this is f(x) of x of f(x, y) of x and y. This was dxy of xi and yi. So I have it xi and yi because it's a discrete. So you have numbers, you have specific values. Here, I leave it without I because it's continuous. It has a lot of variables. So this is gonna look like, let's say, it's gonna be like a hat, like something like this, and also have something in this direction. You see? And it's in the 3D, all right? So if you cut here, you are gonna find that there is a circle, all right? And this is have the highest probability, and here you go to the lowest probability. Okay, so right now I'm done with the jointly distributed random variables. This is how we represent them. Okay. Let's now talk about something called marginal probability. So what is the marginal probability? So marginal probability, basically, you have a jointly distributed random variable, okay? Like something like this, it's f and f(x, y) of x and y. But you don't care about one of these random variables. You want to find out what is the probability of somebody in the sample space that you have having a favorite color is red. So basically, you don't care about the gender. So either male or a female. So basically, you integrate from negative infinity up to positive infinity for the entire sample. You don't care if you are going to stop at a male or a female. So you basically sum 0.3 and 0.067 together. Okay, so if I sum them together, it's going to give us 0.3 7, and this is going to be 0.367, and this is 0.267. If you sum all of these, it's going to give you 1. All right? So basically, you don't care about the genders. So basically, you condense these two variables in just one variable. This is x, y together. So I made these two just one variable and 3 probabilities. Or you care about the gender, but you don't care about their favorite color. So basically you sum 0.3 and these is gonna give you 0.533 and this is 0.467. What is the probability if I picked somebody from the sample space and it turns out to be a female or it turns out to be a male? I don't care about their favorite color. So the probability of males is 0.533 and the probability of females are 0.46. Okay? All right, so that's basically the marginal probability that you want to find out how to get f(x) of x out of f(xy) xy. How can I get this out of this? So basically, we need to find the CGN first, f(x) of x. How can I find this from this? Well, f(x) of x is that means the probability of your random variable x to be less than x, right? And you don't care about random y. Y should be less than infinity. So y can be any number from the infinity until the entire sample. So you have to integrate all over the y. Okay? Basically, I want to know who is male, and I don't care about their color, and either their color red, blue, integrate until infinity, okay? All right, so if I want to actually write this, this is going to be something is going to be something like this. Look at this here. So what I'm going to do, I'm going to do this, the same integration. The integration from negative infinity to x, and here I'm going to integrate from negative infinity up to positive infinity. I'm going to integrate on over the whole sample space in y. Why? Because I don't care about y. I want to eliminate y from my sample space because I only care right now about x. And now my function is going to be fxy of x and y dx dy. But let's just swap the variables. At the end, I only want my function to my function to be function in x. So I want to get rid of y. So y is going to be v, and this is going to be v. Sorry, just 1 second. I have to do it in a separate step. Let's leave this as u and v, all both of them. Let's put this u and v, and this is u and v. And once, like right now, I know the boundary of the integration over y direction. So right now I can have this as a single integration from negative infinity to x. And once I integrate this, this is gonna be something like this. Sorry, and this should be f small. Okay, sorry. Here. This f small. So I integrate the BDF to get the CDF. Okay, so I have fxy, u and v. All right. So basically, when I integrate over the limit of the integration in the y direction, I will end up with having this function fxy. Right now, this function is going to be only function in x. So you only are going to have x, and here you are going to have v. It's a lot of variables, so we need to, and here's going to be dx and dv. So basically, when you have a real function, it's going to be much easier because right now I have everything in terms of a variable. But once I give you a function in x and y, you are going to do it right away. But right now I have it like all in terms of variables. So so at the end, so that means this is my fx of x, and that's basically what I did here to get this function. Sorry. All right, so this is fx of x, all right? Okay, so what I did right now, I'm trying to get fx out of the fxy, and what I did, I put this as the limit of the integration of this part. So my next part is I want to find out fx of x out of this. So if I want to find fx of x, I have to differentiate this with respect to x. So once you differentiate this, you will end up with this integration. If it's double integration, it's gonna be single integration, like from negative infinity up to x, and then you will end up with fxy u, and u is gonna be x. Not sure if this is right. Oh, okay, it's right. So if I want to differentiate this with respect to x, so I'm gonna only focus on this part, because, all right, if I'm differentiating this with respect to y, so I'm getting rid of the integration in the y direction. And if I'm differentiating this with respect to x, so I'm getting rid of the differentiation in the x direction. So if I differentiate this with respect to x, so basically this is gone, and I'm gonna end up with the integration from negative infinity to infinity of f xy, and then I'm gonna have here x, and here v, so u is gonna be x, and then v dv. And this is gonna be integration in the y direction from negative infinity to infinity. Okay, let's see if I wanna do the same thing, but I wanna get fy. So fy of y is gonna be the differentiation with respect to y of fy. And this is gonna be integration over the x direction, not the y direction. So this is gonna be negative infinity, and here's infinity, fxy, and here is gonna be u, and this is gonna be y, and here you're gonna have du.
Should
So-
be 2x to u, I think, not to infinity.
What is that?
The integration should be to,
This one or this
yeah,
one?
this one, the last one.
Okay.
Should be goes to u or x, not to infinity.
Okay, so right now we have this from negative infinity to x,
Yeah.
and this from negative infinity to negative infinity. This is if it's fx. So what I'm saying is, what if I'm trying to get fy? So fy, if I want to write the f equation of it, I'm gonna write it in a small different color. Fy of y is gonna be the integration from negative infinity. It's gonna be over x. All right. So let's put it that way. If you are looking for function in x, you have to integrate all over the variable y. So you need to get rid of y, so that the final function to be function of x. So right now I put negative infinity and negative infinity. If I'm looking for variable y, so I have to get rid of the x, and I'm only integrating over y direction. So this is gonna be fxy, and then I'm gonna have here, this is gonna be u, y, du.
I think you and D.
This is gonna be, I'm integrating over y. So here I was integrating, oh, I'm gonna go u and v, both of them. Because I still didn't, I'm still in the, in fy, so this is gonna be du, and this is gonna be dv. Once I differentiate this with respect to y, ddy, so I'm getting rid of this integration, and I'm getting rid of the y variable, and I'm only integrating from negative infinity to negative infinity, fxy, and it's gonna be over the variable du, which is gonna be over x. All right, so let's put the marginal probability that way. It's a little bit confusing because it's double integration, a lot of variables, but when you have a real question, so fxy is gonna be something like this. Fxy is equal to x squared plus 2y. So basically you are gonna be able to differentiate with respect to x and y. But what I wanna tell you right now, if you have a function in x and y and you only want it to be a function in x, so you integrate over y, okay? So if you integrate it over y, over the boundary conditions that you have, so you are gonna end up with the function as a function of x. If you want it as a function of y, you integrate it over x to get rid of the x, okay? All right, so that's the end of the marginal probability. I believe you might have one problem in the homework as an application on this. Try to do your best in it, and if you have any question, you might come back to me, or we might solve it in that class, okay? All right, so So now I'm gonna talk about conditional probability laws. Can you guys see this? So what about conditional probability? If you guys remember, when we talked about conditional probabilities, we talked about events like probability of event B given A. Do you guys remember what this equal to?
Yeah. P of A intersection B upon P of A.
Intersection A over
P of A over.
probability probability of A. Okay. So definitely probability of A doesn't equal to 0, because if probability of A equal to 0, so probability of A never happened. Okay? And we are looking for probability of an event given an event already happened. Okay. So the thing is, right now what I'm trying to do, I want to convert this to a continuous random variables rather than dealing with discrete random variables. You guys remember from before, you have B as a bunch of numbers out of tossing a coin or tossing like a nerd or something like this, a dice, no? So the thing is, right now, what if B is an event that includes a random variable x less than or equal to x? That's my event. That's a continuous random variable. Like, let's say that I'm looking for a distribution like this, and this is x, and I'm looking only at this part. This is where my random variable x is less than or equal to a value, a signed value x. Okay, so basically this probability starts to be the probability of my event B, x is less than or equal to x, given that an event A already happened, is gonna be equal to the probability of x less than x intersection event A over the probability of event A, right? That is, if it's a continuous random variable. We can write this in that way. Since this is a probability and this is the probability of something less than an assigned value, so right now we are talking about CDF, not PDF, okay? So you can write this that way. You can write it as F, and here I'm gonna write it as Fx, my random variable x, that's what I'm looking at. My random variable x can be any value here, like let's say this is my x. It can be any value from negative infinity until x. So this is the cumulative probability of my random variable x conditioned on A, and then I'm gonna open a parentheses and I'm gonna describe that x is, I'm gonna put the assigned value here. So basically I put this here, and I put the other event here, and I put the assigned value here, conditioned on the event A. So this is like this. So this is how we write them, all right? And this is gonna be equal to the probability of x, my random variable, less than the assigned value intersection A over the probability of A. All right? Okay, so that's still, it's still a probability that the probability axiom still applies to. So this probability should be something in between 0 and 1. Once you integrate this area, so what I'm doing right now, I'm trying to find what is the probability, the cumulative probability of a random variable x to happen, given that it already happened and x is less than an assigned value x. Okay? All right, so this is still a probability that the f should be something in between 0 and 1. And f, what is the maximum value of f? The maximum value of f is going to be less than or equal 1. Like the maximum value of this can be less than or equal 1 when your random or your assigned value is maybe negative infinity. So that basically when the assigned value is equal to infinity. And if you are looking for the probability of your random variable to be in between x1 and x2, and all this conditioned on A, that's something like not only one random, not only two random variables, one assigned value. I'm looking for something in between. Let's put it in a different color. Like what is, if you are looking for something here between x1 and x2, and your random variable somewhere here, x. So you are looking for the probability of your random variable to be more than x1 and less than x2, given that event A happened. So if you want to write the equation of this, this is going to be equal to f, I'm going to find it here, f, I'm going to put it as fx of x2 condition on A minus fx of x1 condition on A. Right? You can actually put condition on A here as well. Alright, so what this means? That means that you are going to get f at x2 is going to give you all the area under the curve in the right side. And if you got the f at x1 is going to give you the area under the curve from the right side. If you subtract them from each other, it's going to give you the area in between them. Because you guys, as you know, that when you have a distribution like this, f is always the area from the right side. The more your assigned value is bigger, so the more the area. Until you go to negative infinity, the area under this curve and the positive infinity is going to be 1. Okay. All right. So let's see an application in structural engineering on this concept. Alright, so right now we have a beam, steel beam, simple beam, has a load Q, and it says that for the beam, this beam shows a sign of deterioration. So this beam is deteriorating, but it's not failed. Okay, like you see some cracks, it's not ruptured. Okay, a sign of deterioration. So the following procedures were conducted. Number one, load test to determine the capacity of the beam. So this beam taken in the lab, and we put a load in this beam to know the capacity of this beam. And subject the beam to load Q, and this Q is equal to RPL. RPL is the rupture load, or not the rupture, it's the proof load, the yield load. But we're not gonna make the beam fail. We are gonna see if it can take the load up to the yield. If you guys remember, the steel is something like this, and you take it to the yield, and then something like this, and this is the rupture load. So this is RPL, the proof load or the yield load, and this is the rupture load R. Okay, where the beam is gonna fail and it's gonna have a lot of deformation. All right. So It says that the beam passes the test. What test? The proof test. Like it passes the yield. Like this beam can take load up to the yield. If the beam capacity is uncertain, you don't know what is the beam capacity. Right now, I know the proof capacity or the yield capacity of the beam because I took it to the test and I determined what is this capacity is. So if the beam capacity is uncertain, what is the probability density function of the capacity? Like let's put this in a distribution. Let's say this is the load on the beam, okay? Something like this. And then you loaded this beam until this load, RBL, the proof load. The proof load is somewhere here, RBL, and it's a certain. So you know RBL. But the capacity load R is uncertain. It's somewhere, let's say here. Okay, let's say this is R, which I don't know. What is the occurrence proof? Okay, so the question is, if the beam capacity is uncertain, what is the probability density function? Or what is the occurrence probability of R given that RBL already occurred? Okay, so the question is, what is the probability of R to happen given that this already happened? So basically, this beam can take load in between this area, right? R, and then I already tested this, I already know this. So somehow I'm looking for something in between this and in between this, given that this already happened. You already know for sure that this beam passed this test. So let's see what is the probability of R to be in between this range, okay? So that's what we are looking for. Let's write this in terms of a probability. I'm looking for the probability of R, like, let's say, let's put it that way. R, that's my random variable.
What's small r and big
Okay,
R?
small r is the assigned value of the capacity of the beam. Capacity is the rupture load.
Okay.
And the beam is not ruptured. The
Okay.
beam, it shows signs of deterioration. So it's uncertain. But this is the proof load, or we call it the yield load of the beam. And we already take the beam to the test, and we tested the beam, and we know what is the proof load is.
And what's the capital R?
Capital R is the random variable. Like this is the R that you don't know. But if we know it, it's gonna be R here, but we don't know it. So do you remember when we say what is the probability of x less than or equal to small x? X is the random variable, and this is the assigned value. What is the probability of your wind speed to be less than 30?
Okay.
Okay, so here, what is the probability of your capacity load to be equal to this value?
But we have this value then, the small r. That's
Yes.
side value, yeah. We have it.
That's a value, but we don't, everything right now is variables, like we didn't put numbers.
Okay.
Okay, so, but in a problem, if I wanna get a problem with numbers, this is gonna have a number and this is gonna have a number.
I see.
But we're gonna leave everything as a variable, and we're gonna get the final answer as a variable,
Okay.
okay? All right, so what I'm looking for, what is the probability of the beam capacity R to be less than or equal R? Like, that's actually the actual capacity. Let's say the capacity of this beam is 100. So what is the probability of R to be less than 100? And given that R is more than RBL. Because right now you know what is the rupture load, and you know that R is somewhere here, not here. Because here, I already know that this is the yield, and if you want to get to the rupture, you have to exceed the yield. Okay? So I want to find out what is this function is. So this means I'm trying to find the probability of R less than R intersection, the probability. Actually, I can write it in different ways. You can put it this. You can put it separate, or you can put it as this. And R is more than RBL. What is the probability of your random variable or the capacity of the beam to be more than this and less than this over the second one, the probability of R more than RBL. That is the rule, the probability of A given B equal to the probability of A intersection B over the probability of B. That's basically the way it is. All right, so this can be put in a different way as we put it over there. We can put it as F, and F, I'm gonna have R conditioned on the R more than or equal to RBL. So I can put it actually FR, like if you don't want to write this part, that's fine. So what I'm looking at the CDF of R, but I put the condition here. And then here I'm gonna write something, I'm gonna put F here and F here. I'm gonna convert these into two F's. Do you guys remember when I did this? I didn't do it here. Okay, so I'm gonna do it here. If you guys remember, if you wanna find the probability, this here is gonna be something like you can find, this is FR of RBL, and this is FR, but this is F small, because that's the BDF. And here, this is FR of R. If you want to find these two probabilities, you have to subtract FR of R minus FR of RBL over this one. This one is a little bit tricky. You guys are gonna tell me, how can I find this?
It's 1 minus.
1 minus. Why? Because this one, if it's a small, like if I'm looking for R less than RBL, yeah, if I'm looking for R less than RBL, so it's gonna be this part, right? This part is RBL, right? If you're looking for R more than RBL, so it is the rest of the distribution, and the rest of the whole distribution is 1, so this part is 1 minus this one, so this is gonna be 1 minus FRRBL. So right now I have F, but I'm not looking for the CDF, I'm looking for the BDF. So the BDF is FR of R more than RBL, because I'm looking for the value of R, how it's gonna be. So this, as you know, if you wanna find F out of the F capital, you have to differentiate this with respect to R. R is the variable that I don't know, and I have to differentiate FR of R when R is more than or equal to RBL. And you have to put here, oh, here, sorry, I forgot to put the random variables in parentheses. Like I forgot to put these stuff, so let me put it here because it's very long. I'm gonna put it here, F, and here I have F of R. Given that R is less than or equal to RBL. And here I'm gonna put my random variable that I'm looking for is R, given that R is less than RBL. That's how we write it. If you want, like, just to put this as FR, that's fine. We are looking for the cumulative distribution function in the random variable R, given that R, the assigned value, which I don't know, given that R is less than RBL. So, and here is the same thing, but it's a small part, the small f, FR, and we have here R less than of RBL. Okay?
Here are more than RBL.
Oh, yeah, sorry. Because we are looking for. All right, so if we want to find this, we need to differentiate this function. And I'm gonna write it the same way that I put it here. The function f of the random variable r, given that r is more than RBL. Can you guys differentiate this function? This is function, okay, look, we have three terms. We have this term, we have this term, and this term. What is the derivative of the f capital? If you have an f capital, if you differentiate it with respect to r, it's gonna give you f small r. If you differentiate this function, but look at this function is function of a constant, a value that you already know. It's not a variable. You already know this thing. RBL, you already know it. But this one, I don't know it yet. That's uncertain. So this one, when you integrate, is gonna give you 0. So this is gonna stay minus 0. And if you integrate, by the way, this part is like a constant. This is the same thing. Like if you put this function, like if you try to expand it, it's gonna be fr of r over 1 minus fr of RBL, and minus fr of RBL over 1 minus fr of RBL. So what I did, I separated this into two parts. This part is all constants. There is nothing is variable here. I already tested this and I know this, and I can substitute in this function, and I can have a number here and a number here. So when you differentiate this part, it's gonna give you 0. When you differentiate this part, all what is under here is constant with the random variable here, so it's gonna stay as a constant. So when you integrate it, okay, what I wanna do, I wanna put the integration here, dr of this. So the integration, the differentiation of this is gonna be the small fr of r over 1 minus f capital R, sorry, RBL. Oh, sorry, this is R. And this is fr of RBL. And this is gonna be 0. When you integrate it, minus 0. And then I can remove this part. So the final answer of this question is going to be the BDF FR of R, given that R already more than RBL, the rupture, the yield load is going to be equal to FR of R over 1 minus FR of RBL. So what that means? That means if you want to find the probability of your random variable, the capacity of the load, to be less than condition on to be less than R, given that R already more than RBL, is going to be equal to this part. That's what this means. But sorry, no, this is not this one. This is if you want to find it equal to, because I want to find if R, my random variable, is equal to this one. When I put it, this one is less than, I put this one, which is the F capital, the CDF. And what I'm trying to find right now, it is the BDF. Okay? All right, so I would just want to wrap this up. So this is finally is going to be equal to 1 over 1 minus FR RBL multiplied by, so what is this? By the way, this is FR of R, and this is FR of R, okay? What is the difference between them? This is FR of R, not conditioned on anything. That is the probability of your random variable to be equal to the capacity. Okay? But this is the probability of your random variable to dependent on already your capacity exceeded the yield load. And if you guys remember, we called this something before. We called this before as prior, and this one is a posterior, and this part we call it as likelihood. You will be given what is the probability of your random variable to be equal to the capacity, and you want to find the probability of your random variable to be equal to the capacity given that something already happened. So you got more information about your problem. So before you did your test, you didn't know. But once you did your test and you know for sure that the capacity is more than the yield load, so you are gonna have more information about the yield load. You multiply it by the prior is gonna give you posterior, different data, okay? I know it's a little bit tricky with all the differentiation, integration, and random, and a lot of numbers, but you have to be on top of the variables that you are using. And I have everything here. Like if you look here, I'm trying to expand it. Hopefully I make it less complicated. But if you look here, it's like maybe 3 lines of equations. That's it. Like 1 line, 2, 3, it's solved. Okay? But I'm trying to draw some graphs so that you can see, understand how to solve the problem. Okay, so we have 10 minutes. I'm gonna have a little bit of introduction about something that's called functions of random variables.
Actually, I have a question about the yielding.
Okay.
So when you say that the capacity gonna reach more than yielding, that's coming from the tests, which is maybe 100 tests we did.
No, we only have 1 test. And in this, like we took this beam. This beam is deteriorating, it's not failed, okay? Because if it's failed, I mean like I already know the capacity, okay? I mean like if I test it until failure, I'm gonna know the capacity, but I didn't do this. I test this beam until I get to the yield point and then I stop the test.
Okay.
1 test, and then I got this value, RBL, okay? And this beam definitely have a capacity, and this capacity is R, all right? So what I'm looking for, I wanna find what is the probability of R, of the capacity to happen, given that you already know that the yield already happened.
But isn't it gonna reach capacity for sure?
That's why we have it as a probability, it's not deterministic. So at the end, you are having the final answer as a probability, not for sure.
But
No. If it's 100%, it's gonna be for sure.
But I mean, if it was a steel beam, for sure it's gonna reach the capacity and fail, or is it gonna be?
But the beam is not failed. The beam is deteriorated. Let's see when this is gonna be 1. Like this is gonna be 1 if this can cancel this and mean that this is gonna be equal to this. Like the rupture is equal, the yield is equal to the capacity. You know what I mean? But the thing is, we don't know the capacity. That's why we have this problem, to find the probability of R is the probability of R is equal to your capacity load, given that R already exceeded this. The thing is, I said that R is here, right? Okay? But your random variable that you are looking at, you already kept testing until you reach it that one. If you want to find a failure, you have to keep increasing the load, right?
Yeah.
Until you reach this, but you don't want the beam to fail, okay? But you know that R, the loads that you are putting on the beam and you are increasing it, at some point it's gonna reach to R, but I don't wanna make it to reach to the failure. So that's why we're using the concept of probability to find what is the probability of failure. Given that R, something that I already know, exceeded the yield, okay? And given that R, and I wanna find the probability of this to be equal to this. That's what I'm trying to find here. So this The F small means that the probability of R equal to the capacity load, given that R already exceeded the yield curve. That's what I'm trying to find, without failing the beam. You know what I mean?
I understand that, but there is some confusion.
Absolutely. When I took this, I didn't understand any of this. So it's good that you. I had he's a good professor and everything, but he would just fill the board. Nobody asked questions. Tried to ask questions, and I didn't ask anything. So, but yeah, maybe you will take this home. Try to focus. It's a little bit like it needs, because the probability concept and all this, it's kind of philosophical. So don't want to say philosophical, but it just like need you to like understand, have really good grasp on the probability concept. Okay? And if you want to expand your knowledge, you might check the textbook about the conditional probability with continuous random variable.
See, thank you so much.
Yeah. Okay, so I don't think we will have enough time to talk about the functions of random variables, but what I'm gonna say is functions of random variables we're gonna discuss it next time, but let's say that we have a random variable x and you made a function gx, and this gx is equal to x squared plus 2x. Gx is still a random variable, but it's a new random variable. Okay? Like let's say that you have a beam has a load Q, and then you try to find what is the load here. The load here is Q over 2. That's still a random variable. If you put a distributed load W, Q is a random variable, and W is a random variable, and you try to find the load here is going to be WL over 2. So the reaction R, which is equal Q over 2 plus WL over 2, this one is still a random variable because it's a function of two random variables. What are these two random variables? Is Q and W. L, the length of the beam, is deterministic, is not random variable. Okay? So next time we are going to see how we can solve or how we can understand functions of random variables and how we can deal with the probability density function and the cumulative density function. All right? I know it's a lot of integration and a lot of variables and less numbers, and we engineers like to deal with numbers, but in the homework there will be numbers, and you are going to just see how is the one in the variables look like and try to fit the numbers inside the variables. Okay? All right, see you guys next week. You are the one who's doing the paper. Who's going to do that? It's all your group, right? Or are you going to explain it from other groups that has
Thank you.
like the other groups that have, because they have different spacing, you want to increase the parameters?
Yeah, remember we had, we were supposed to do that, but we limited.
Yeah, I know, but if you want to expand it and see other parameters, like, I know that everyone has different spacing. Like you has 3, other has 3.5, we can add a new curve. Your problem if you, but I believe some of them has problems with the model, but maybe it's not that big.
I know one right there.
Yeah, but I mean, if the output is gonna serve the paper is gonna, it might be good. If you want to.
Yeah, I'll look into that, I think.
في مواد نثبتها وبعدين مع التطبيق الثاني عشان عمل predicting
Yeah, because they're gonna have comprehensive results.
Mhm. Yeah, I'll look into that and like I said, probably also do.
But by the way, I wanna tell you that this is a barometric study, so don't get your hopes up.
Thank you.
Have a good day.
As far as,
It's a barometric study, so it doesn't add much knowledge like you didn't develop methodology.
Right.
You just investigated some parameters. So the thing is, so the thing is,